Now, in today's lecture, we will be continuing with the position sensors. Last week we have discussed resistive sensors and two inductive sensors. Today I will finish just briefly with the third inductive sensor, and then we'll go to other principles. So the sensor that you can see on screen is also an inductive sensor. But this sensor is useful if you need to measure small distances. So if you are looking to measure very accurately the distance, let's say approximately under 1 millimeter or even less, we are looking to measure the distance of this air gap. So this air gap is what we want to measure, and the object that is the sensor is attached to a frame, and to a frame we have attached this ferromagnetic core, this U piece of material, and to the object that we measure we attach the armature. So this armature, this piece, is attached mechanically to our object. If our object is ferromagnetic, for example if it's a piece of iron, then we don't need the armature, and the object itself can be used as a part of the sensor. The way it works is that here on top we have an inductor, and we power this inductor with electric current. This electric current needs to be AC current, and this AC current will induce or will create a magnetic flux in the core. So here we connect some AC power supply with some voltage and with some frequency, and this inductor will create a magnetic flux. The magnetic flux will flow in the ferromagnetic core, so it will flow like this in this U piece, and then it will flow through the air gap, and it will flow through the armature, back to the air gap, and back to the iron core. So the core needs to be from a ferromagnetic material, because we want that this conducts very well the magnetic flux. The inductor parameters are the inductance L and number of turns N. Those are the single parameters that we actually need to calculate everything. Now we also need to know what is the cross section of the iron core, so we'll call that A, and we need to know what is the size of the air gap. Now in fact in this magnetic circuit we have two materials. One material is the iron, which is here in this U piece and in the armature, so this has some magnetic properties. And then the second material is the air, which is here in the air gap. So we make use of the significantly different properties of this ferromagnetic material. As we are getting closer with the armature to the ferromagnetic core, this air gap is getting smaller and smaller, and we can describe the dependence of inductance of this whole circuit as a function of this air gap. The air gap initially is of size delta, and then it can change by plus minus delta. This is called a small air gap sensor because this principle works only for small distances, and it works when this delta is smaller than, let's say, 1 millimeter, but maybe even smaller than this one. If the distance is larger, then this sensor will not measure at all. So now let's take a look on how we can actually calculate the inductivity of this circuit. This circuit has the inductor here, and it has an iron core, so we can use formulas for an inductor with a magnetic core, I will just write them here. So it's L equals N squared, that is the number of turns, over the magnetic resistance, and we'll call that Rm. And the magnetic resistance here actually has two components in our circuit. Here we have this component, this is the iron part of the circuit, and this is how the magnetic flux is flowing. And then the second component is the magnetic resistance of this air gap, and here we see that it has a different material. Now in the general case, the magnetic resistance, it's a very similar formula as for electrical resistance of some wire. So this magnetic resistance depends on the material, it depends on the cross section, and it depends on the length of the magnetic circuit. So if we make this cross section larger, then we have a smaller magnetic resistance, so A will be here, and the material dependence is expressed by the permeability. This is a constant of the material, and here we have the length. So in the case of the iron, it's the length of the from here of this whole this length of whole this red curve. And in the case of the air gap, it's the length of this blue curve. So if I will write the equation just for the air gap, it will be delta here. So we now have one component. The constant mu is given by this formula. It's mu 0, which is the permittivity of vacuum. So it's a very small number. And then the material constant is called mu r. It's called relative permeability, and it is given by the material. The relative permeability of air, so here in this air gap, is very close to 1. In fact, by definition, vacuum has 1 exactly. For air, it's very close to vacuum. It's 1 and then few zeros, and then it's just some number at the end. So we can safely say that it's 1 for the air as well. On the other hand, the permeability of iron, so this part shown in red in the circuit, is very high, and it can be more than 1000. So there is a significant difference between the permeability of air and the air gap. However, if we calculate the magnetic resistance of air in the air gap and of the iron, we will find out that the magnetic resistance of air is much larger than the iron resistance, and this will deform us the characteristic of the sensor. So we can divide the characteristic of the sensor in 3 regions. This is how the steady state characteristic of this type of sensor looks like. If we would derive the formula for current or inductivity, which we will not do, then we'll find out that we need to make some simplifications in the calculation. One simplification that we need to make is that here in the linear region, in this linear region, we have some air gap, and the air gap resistance, this is the magnetic resistance, is significantly larger than the iron resistance. So here this air gap has some value larger than a minimum value. So we need to operate not from 0 with this air gap, but from some minimal distance. Now if this condition is not fulfilled, then the air gap resistance is having a similar size as the iron resistance, and then we are in this region where we don't have a linear dependence between the current in the coil and between the air gap size. So this type of sensor has always some minimal delta. Then in this region we have a fairly linear response, and in this region is where the sensor is operating. So in this region the condition is met, the air gap resistance is significantly larger than the iron resistance. And then when the air gap is too large, when this armature is far away from the iron core, we have a second limitation, and this relates the AC circuit. Here this is a formula of electrical properties of the circuit, and here we are comparing the impedance in the inductor. Here it's omega L, it's called inductive reactance, and we are comparing that with resistance, because every wire here in this coil has some electrical resistance as well. And in this region, when we have a large air gap, the magnetic circuit is not closed anymore, so the magnetic flux does not flow like this through the air gap, but it flows like this and then directly through the air, because the armature is very far. So this is not anymore an ideal inductor with an iron core. And then in this region we see that even if we increase the delta anymore, then we don't have any reaction from the sensor. This delta max, as I've already said, is about 1 millimeter. So let's say between 0.1 and between 1 millimeter, that's the region where this sensor can operate properly. As I've already said, then this armature can be the object itself. So if we use a ferromagnetic object, this sensor can be used, for example, to measure the thickness of paint that we have on the surface. So this could be the object itself, and the air gap will in this case not be the air gap, but it will be the layer of paint. And if we know the permeability, which is also very close to 1, then we can measure the thickness. So this sensor is used to measure small distances, and it can be used also for other purposes, such as thickness measurements of some layers. So that's all for inductive sensors. And now we will start a fairly large group of capacitive sensors. So this is the third electrical property that is used in position sensing. This capacitive principle is very useful, because it is used not only to measure position, but it is also used in many other sensors. It is used in pressure sensors, it is used in acceleration sensors, it is used it is used in force sensors, and so on. So the capacitive measurements is very important because it's used almost everywhere. For example, also liquid level. If you want to measure some liquid level in a tank, this can be done also with capacitive sensors. So almost in all regions of sensor technology, you can find the capacitive principle. The way it works in principle is very simple. We are looking for changes of capacity. Let's imagine a capacitor like this one, and here we have some distance between the electrodes. We'll call that always D. We have some area in the electrode, so that will be the area here. We'll call that A. And we have some material between the electrodes, and the material will be defined by a constant of the material, which is called permittivity. Now for this capacitor, we can calculate the capacity based on this formula. So epsilon 0 is vacuum permittivity. Here you can see the value, it's a very small number. epsilon r is called relative permittivity. So this is a material dependent constant. And A is cross-section, and D is distance between the electrodes. We can see that if we are increasing the area of the electrodes, we have increasing capacity. And if we use the changes of area, then we will have a linear dependence of C on A. If we change distance, then we have a nonlinear dependence of C on D. And the third possibility is that we would change the material, so we would change epsilon r, and this would give us also a linear dependence. Now epsilon r is a material constant. It is a function of properties such as temperature and pressure, but we will in most cases have problems with temperature changes. So let's take a look on this table. This gives you some examples of permittivities for different materials. So by definition, vacuum permittivity is 1. If we are talking about air, then it's in this respect it's again very close to vacuum. So it's 1, then few zeros, and then some number. So we can say that with a good accuracy it's 1 as well. And the other materials, for example paper, 3.5, silicon, and so on. In the example of water, I would like to show you the dependence on temperature. So here for 0 centigrades we have 88 relative permittivity, which is fairly high, and this allows us to detect very easily water level with capacitive sensors. As the temperature is increasing, then the permittivity is decreasing. So for example, for 100 centigrades, here we have 55. So this is a significant change. That's almost a little bit less than 50%, about 40% of change of relative permittivity. So in many cases, if our capacitive sensor is to be operated in a large temperature range, we need to have a temperature sensor as well, and we need to store the table that has this relative permittivity measured somewhere. So let's take a look on how we can actually use this to measure position. I will start with the change of distance. Here we have the capacitor that we use to measure the distance. We are looking for the distance d between the electrodes, and we have one electrode that is fixed. That's the left one here. So this electrode is fixed to a frame of the machine, and the second electrode on the right is movable, and this can go with our object, or it could be even the object itself if it's conductive. As the object is getting closer, then d is decreasing, and based on this formula we can see that the capacity is increasing. We keep the material constant, so this is a constant number, epsilon r. We have the constant area here, A, and we are only changing d. Now if you plot this dependence in a chart, it will look like this. So here, if we are decreasing the distance, then C is getting larger and larger. And here, if we are increasing distance, then D is getting smaller and smaller. We can define sensitivity at any particular point of this curve, and sensitivity is nothing else than the slope of the tangent. So if I make a tangent, for example, at this point, then it has some slope. If I make a tangent here, it has a smaller slope. So we can see that here, when d is quite small, we have a larger sensitivity than here when the d value is larger. So we can see that the sensitivity is decreasing. Moreover, here, if we would continue with the curve, we would see that it gets flat, and here we have no sensitivity at all. So for this reason, we can use this sensor only when D is very small. And in fact, this principle of sensor is very accurate for the smallest distances. I will later show you some examples, but this is the most accurate type of measurements for position. We can measure up to several nanometers of resolution. We can measure up to the size of an atom, for example, with this capacitive principle, where we are changing the distance. On the other hand, we cannot use this principle for larger distances. So if D is larger than, let's say, 1 millimeter, maybe 0.1 millimeters, it cannot be used anymore. So this is for very, very small distances only. So this is how it's used in position sensors. Very often, this capacitive sensing is used, for example, in acceleration sensors. And in this case, it is not based on a single capacity, but it is based on differential measurements. This approach is called a differential capacitor. The way it works is that we are still looking for capacity that we have in the circuit, but now we have two capacitors. We have capacitor C1, which is between the electrode on the left and the one in the middle, and C2, that's between the middle electrode and between the electrode on the right. Now the two electrodes here on the right and on the left, they are fixed to the frame, so those two electrodes are not moving. And we move the central electrode. So this electrode in the middle is attached to some movable object. So it could be a spring, it could be a mass, for example. And when this middle electrode is moving, let's say it will move to the right, then we are decreasing D2 and we are increasing D1. So C2 will be getting larger and C1 will be getting smaller. Now we do not evaluate directly the capacities, but this is connected in a circuit that's called a bridge circuit, an AC bridge, and we are looking for the voltage. So this will give us the voltage that is a function as the out of the input position. If we plot independently the dependence between C1 and D1, or X position, then it will look like this. So this is the same response as we have seen in previous slide. So here we have this shape and a linear dependence, and X in this case is getting to the right. So D1 is increasing and C1 is decreasing. And here we have a similar chart for C2, and again it's going to the right. So here D2 is decreasing and C2 is increasing. Now if we do this like this in a separate way, then that's not too much of use. But if we combine it in a differential bridge circuit, then the output voltage will look like this. It will combine those two charts together, and we will have a better response. Why is it better? Well, here around the origin, we see that it's a fairly linear region. So when we are not too much off from the central position, then we are in this linear region. And also we can see that we have zeroed here the output. So here when we are exactly in the middle, the output is going to 0. So the way this is used is that we have a set of those electrodes, and we measure the output voltage from this connection. Again, it is used only for small distances. So this distance, the distance between the electrodes, can be a few micrometers, 10 micrometers, 50 micrometers, something in this range. And typically this kind of sensor is embedded directly in an integrated circuit. So it's made from silicon, and at the end it forms an accelerometer. We'll see examples in some of the next lectures when we will be discussing acceleration sensors. Okay, so that's the change of D. In both cases, it's possible to use it only for small distance. So the D is small. And we have a non-linear dependence. On the other hand, the approach when we are changing the area between the electrodes will allow us to work with larger distances. It could be even few meters, and moreover we will have a linear dependence in some region. So the way it works is that we have again one electrode that is fixed. This is fixed to the frame, and the second electrode is moving with our object. So now our object is moving in the vertical direction like this, and we keep the distance between the electrode in a constant value. So D is not changing. If you remember the formula for capacity, then it's clear that this has to be directly proportional to the area. So the area now is the area between the electrodes over there. And as we are changing the position, we are changing the area as well in the circuit. So we typically have this kind of dependence. We have the distance x here, and when we are moving the electrode, we are increasing or decreasing the capacity as we are increasing or decreasing the area. And typically there is a region here around the origin when the electrode is far away from the fixed electrode, and here we have constant capacity, and we don't see any change of the capacity based on position. So this is a constant capacity given by the cable capacity, connectors, holders, and so on. So this is small value. Anyway, this is used for larger distances. It can be even a few meters, and it can be used also for liquid level sensing, for example. And the third possibility is when we have to change the material in our circuit. So in this case, here we have two fixed electrodes. So now they are attached to the frame, both of them. And we are inserting here a different material. Now this works only if the difference between epsilon 1 and epsilon 2 is significant. So for example, if epsilon 1 is air, and this would be material with permittivity of, let's say, 1.2, for example, polyethylene pellets have this small permittivity, and we cannot use this principle. We need a material where epsilon 2 is significantly larger. For example, this could be water. So this could be a very good liquid level sensor. Here we are filling the water between the electrodes, and we are looking for capacity changes as the electrode is filling the space between the electrodes. So this is typically used in liquid level sensors. We can again calculate the capacity. Here you can see the formula. Epsilon 1 is the permittivity of the material that we have here above the, let's say, liquid level, or above the second material. We are assuming that the distance and cross-section is the same in this region, and here we have the difference between the permittivities. So we can see that if this difference is small, then this part is almost zero, or zero even, and it does not contribute at all to the capacity changes. So for this reason we need to have this difference as large as possible. This principle works with very large distances, so it could be a few meters. So because here this could be a tank, where we have just 2 electrodes, and this could be the liquid level. And second advantage is that we have a fairly linear response as C versus the position. So we have covered 3 principles. They are good for different ranges and for different applications. We will see the capacitive sensing many times in the future. Let's take a look very briefly on something that is used for liquid level sensing typically. This is a cylindrical capacitive sensor. Now the formulas that are shown here, you don't need to remember them at all, but it's shown here only because I want to show you that it has a very similar structure to the basic formula of the capacitor. Now here we see such a cylindrical capacitor. Here we have an electrode in the middle. Here we have an electrode that is a cylinder. So for example, this could be a tank, and this could be an electrode in the middle. And we can either move the electrode, so we would change the length here, or we could change the material, so we could fill this tank to a certain level, and then we could measure the capacity. Now if we derive the formula for this capacitive sensor in a cylindrical shape, we will see that it has this structure. And here we can see that it again depends on the material, shown here as known as epsilon. Under epsilon here it's this is epsilon 0 times epsilon r. Here on top we see length, and this is basically the area here that we have in this position. And here we see a logarithm of the distances, so d1 over d2. So this is telling us what is the distance between the electrodes. So we can see that it has a very similar formula. This is the cross section and this is the distance. So it will have similar properties as all the other sensors we've seen so far. If we plot this dependence in a chart, we will again see it's very similar to the one when we have changed the cross section. We are changing the position X, so for example we are moving this electrode into the sensor and out of it, and it has this shape, so we have some linear region where we actually use the sensor, and here we have some non-linear region and some constant capacity of the cables and of the connectors. So we will see this again when we will discuss liquid level sensors, because this is used very often as a liquid level sensor. Here are a few examples of industrial capacitive sensors. Now some of them are for continuous measurements. That's the sensors here shown on the right. I will focus a little bit more on them. And those two here on the left pictures, those are called proximity sensors. And we'll be talking about it as well, but we'll do it next week in the next lecture. So let's focus on those continuous capacitive sensors. Where can we actually use them? Now, those continuous capacitive sensors that are, well, at least the ones shown here, are based on the distance changes. So they work in a very small range, 10 micrometers, 20 micrometers, 50 micrometers, something in this range, but they are able to achieve a very high accuracy. Typically you can achieve an accuracy in nanometers, so you can measure very small distances. For example, the sensor shown here on the right, it has a range of 20 micrometers, so this is the maximum distance it can measure, but it has a resolution of 0.2 nanometers. So we measure the distance between the sensor and some surface, and this distance can be measured with an accuracy of 0.2 nanometers. Now, to give you an idea how small this is, now the size of an atom is somewhere between 0.1 and 0.5 nanometers. This depends on the element, of course. So with this kind of sensor, we can measure within the resolution of about 1 atom. So this is the most accurate measurement. It's even more accurate than optical measurements, interferometers, for example. It's a very accurate way of measuring distance and position. A second example is that here we can measure tilt. So if we use two sensors like this, then tilt is nothing else than the distance measured at 2 points, and we can calculate what the tilt is. So here is such an example. We measure this distance, we measure this distance, and we know what is here the distance between the sensor, and we can calculate what is the tilt. So in this case, here again one example. This is again a capacitive sensor. This one has a range of 100 micrometers, and you can see what is the resolution. It's even smaller than 1 atomic size. Those are values that are obtained from the data sheet directly from the manufacturer. So you can see how accurate it is, and how it's possible to use this capacitive sensor. We can also measure the thickness of some layer, again with a very high accuracy. This is again using an example of such a continuous sensor, and the point here is that the layer has to be non-conductive, and it has to be made on a conductive surface. So this is a conductive surface. Could be aluminium, could be copper, could be iron, for example, and this is the non-conductive layer. So this could be, for example, a layer of paint. We approach the sensor, and now here we have one material, the air, and here we have another material, that's the paint. And if we know what is the permittivity of those two materials, we can accurately measure the distance between those between this electrode in the sensor and between the second electrode, which now in this case is the object itself. So it could be used also to measure thickness, not only distance. The last example, we can use it to measure vibrations. So now if our sensor is fast enough, then it will be able to sense the movement of my object. So let's say this is a beam, and now this beam is moving up and down with vibrations, and I can sense this distance with this capacitive sensor. So it can be used also as a sensor for vibrations. So now that's all for capacitive sensors. We'll come back to them a little bit later next week, because we'll be discussing proximity sensors again, but not again, but we'll use again the capacitive sensing as the detection mechanism for proximity sensors. Now let's talk a little bit about microwave and optical sensors. So we'll be talking about radars, or in general, let's call it a distance sensor, because this does not have to be only a radar in a sense that it measures the distance of an airplane, for example. But those microwave sensors, radars, are used quite often in industrial systems as liquid level measurements, as distance measurements, as position sensors in general. The way it works is that here we have a transmitter. Now this transmitter will transmit a radio wave. This radio wave will propagate through air. It will hit the object that we want to measure. It will be reflected, and it will go back to the environment, and then we will receive it with the receiver. And we are looking for the distance between the sensor and between the object. So we are looking for the distance x. and this distance can change as this object is moving. Now, there are basically two methods how we can do this. The first is called time of flight. We send a signal at some specific time. Now the signal is propagating here, reflected and propagating back, and we are looking for the time difference. So we send it at time 0, and delta t gives us the distance of the object, because the farther the object is, the larger the value of delta t. Now the signal that we have here is an electromagnetic wave, and this propagates with the speed of light, which is approximately 300 meters per microsecond. So we can see that the time difference, the delta t here, will be very small. It can be below a picosecond, for example. So if it's a very small number, then a small value of time, it will be very difficult to measure. So the time of flight method is used for larger distances. And for larger distances we don't have this problem, because this time is relatively high. It could be picoseconds or more. If we want to time this for small distance, when the distance between the sensor and object is small, let's say if it would be a few meters, then this time would be very small and it would be very difficult to measure it accurately. So in this case we will use the second method, which is called a frequency-modulated continuous wave, FMCW. So the FMCW method is typically used for small distances, whereas the time of flight method is used for larger distances. Now let's take a look on how this FMCW method works. The way it works is that we do not send a pulse of the signal, so it's not like a beep, and we are not listening for the reflection, but we send a signal that is continuous. So here from this transmitter we send a continuous wave. What we do is that we vary the frequency of this continuous signal. So if we plot this as a frequency versus time, now it looks like this. We start from some initial frequency, and then the frequency is sweeping with some defined speed, and we are increasing the frequency. So this is the frequency that we actually transmit. You can see it here, an example. Here this wave has a smaller frequency, and here we are increasing and increasing the frequency. So here we have large frequency. Then we jump back to the initial lower frequency, and then we sweep it again. So this is how it looks like. It's a sawtooth signal. So this is frequency versus time. The frequency sweep actually depends on the used frequency of the sensor. Today, for example, sensors for autonomous cars, they use frequency around 80 gigahertz, and in this case the sweep is few gigahertz. So for example, between 77 to 80 gigahertz could be this frequency sweep. So this repeats again and again. Now we are sending a continuous signal from the transmitter. So this is now the continuous wave. Here is the object, not shown on screen, but let's say it's the corner of the screen. And now this signal gets reflected. So when this signal is reflected, we will also receive a continuous wave. But there will be a time shift, a time delay between the frequency that we are sending right now and between the frequency that we are actually receiving. So the received frequency will have exactly the same shape, like this. We can see that it's again changing the frequency as a function of time. But this delay, this round trip delay, will be a function of the distance. So the farther away the object is from the transmitter and receiver from the sensor, then the larger will be the round trip delay that we have here in this chart. Now the reason why we do this is that we can now compare those two frequencies in a very simple circuit, and we can find out what is the frequency difference. So the way it works is that we compare the frequency that we, let's say we are at this time, for example, and at this time we will compare the two frequencies together. So let's say this time we have this frequency that we are transmitting, and we have this frequency that we are receiving, and the frequency difference is directly proportional to the distance of the sensor and the object. So we have changed the problem of very short times into the frequency problem, and it is very easy to measure the frequency difference. Here a circuit that's called a frequency discriminator is used, and this frequency difference is typically in the order of a few kilohertz. So it's relatively easy to measure this frequency difference. So here the output of this circuit is the frequency difference, and this is directly proportional to the distance. Now it has one disadvantage. The disadvantage is when the distance between the sensor and the object is too large, then this distance between the signals, between the frequencies of the signal will be large as well, and it can even skip one period. So it can, for example, this peak could be related to this peak as well. And in this case we are not able to distinguish if the frequency difference was given by this distance or by this distance that we have here, and we cannot distinguish that. So we have a limited range, and the limited range is limited by the frequency sweep that we have actually available. So this is the limitation of such sensor. Now this FMCW is used quite often in industrial sensors. The used frequencies are in the gigahertz bands. Here you can see what ranges are typically used. Today there is one more band that is being used for autonomous cars. That's about 70 or 80 gigahertz frequency. But industrial sensors, they still use this little bit lower frequencies. This principle can be used for conductive and dielectric surfaces, so we are not limited only to ferromagnetic materials or just conductive materials. And in industrial sensors, the typical resolution is around 1 millimeter, but in a range between 300 and 1000 meters. Of course, if you want to measure 1000 meters, then we will not have an accuracy of 1 millimeter. So this 1 millimeter applies more or less for the lower range here, 300 millimeters. Here you would have a distance, you would have something like few meters accuracy. This is how the sensor looks like. So some sensors are used, for example, also in law enforcement. So this is a sensor that's used to measure the speed of a car. It's a radar sensor, and the two others shown here are industrial radar sensors used for liquid level measurements. We can see the antenna. The antenna is this cone here. This then sits in a tank, and this is the electronic circuit that measures the distance. In this case, the antenna is over here, so again this can be used as a liquid level sensor, and this is the electronic unit that evaluates the signals. So those radar sensors are not only used for position sensing, but they are used also as liquid level sensor. We'll see them again at the end of the lectures, at the end of the semester, where we will discuss liquid level sensing. Okay, and now the last chapter for today, and we'll be talking about optical sensors. Now, optical sensors are used quite often in machinery. If you are building a CNC or some more accurate machine that needs to have position sensors, then most likely you will have this kind of optical sensor. Now I will show you two examples. We'll both call them encoders, and the one that you see on the screen is called Incremental Rotary Encoder, or IRC in short. Now this is called an incremental encoder because this is a relative sensor. Last week we have discussed what is the difference between relative and absolute sensors. An absolute sensor will give you the correct distance between the sensor and the object after powering it up. The relative sensor needs first to go to some zero position, and from this zero position we can count pulses that are coming from the sensor. And this IRC is a relative sensor, so we cannot tell what is the absolute position. When we have an IRC on our machine, we first need to go to a zero position, or say that this is the zero position, and then we can count the pulses from the sensor. How does it work? Now this is a tape where we have a transparent and opaque field. So we have a transparent field, we have an opaque field. So this is transparent, this is black, for example. Then we have a fixture that looks like this, and this has a pair of an LED and a photodiode, and we have two sets like this. So this yellow circle means that from one side of the tape we have an LED, and from the other side we have the photodiode. So we are looking if the light from the LED can pass through the transparent field, or if it is blocked by the opaque field, by this black field. So the output signal that we will get is a rectangular signal, and we will be counting the black and opaque fields as this is moving. Now the tape with this black and white fields, this is fixed. So this tape is fixed to the frame of the machine, and now this fixture, it's called a mask, is moving together with the object. So this could be attached to the axis of your machine, for example. Now note that we have two sensors. Here we have one sensor like this, and the same setup is shown here. Now typically the sensors are shifted by 1/4 of the pitch between the black and white fields. So this is typically 1/4 of this. If I now know the distance between the lines, I can measure what distance did I make with the sensor. So I zero the sensor, and if I move it, I can count that I have seen 1, 2, 3, 4, 5, 6 fields, for example. And if I know how many I have passed, I can multiply that by the pitch, and this will give me the distance. So I'm counting the signals. Now the reason why we have two sensors like this is that we need to distinguish if we are going left or if we are going right. Now if we would use just one sensor, if we would go just with, for example, with this sensor, and let's move it to the left, we see black field, white field, black field, and so on. And by counting we can get the distance, but we cannot get the direction, because we will get exactly the same signal if we move it to the right. We see black field, white field, black field again, and so on. So here we need to have a second sensor, and this sensor, since this is shifted by 1/4 of period, let's say let's say now we are moving to the right here, so we see black here, and then we see white from this first sensor. Now if we move to the left, we see white, and then this sees a transition from black to white. So if we plot the signal as a function of time, and for one direction we'll see something like this. We'll see a rectangular signal going like this. Let's say this is signal A, so this is coming from this sensor, and this will be coming from the second sensor. This will be signal B. So for one direction we'll see that B is phase shifted like this. So let's say this will be for right, but for the second direction B will be phase shifted like this. So there is a phase shift, this is time, and we can see that now if we compare that the B here and B here, we see that there is a phase shift. So the way this works is that we look for the transition at let's say for example the rising edge of signal A. This is falling edge, sorry. So here we see that we have 1 on B, and if we would do this on the second direction, it would be somewhere here, and we would have low in this position. So it's fairly easy to distinguish with those two sensors if we are actually moving left or if we are moving right. Now if we plot this in a chart, the signals look like this. So this is for one direction of rotation. The sensor can also have two tracks like this, and then the black and white fields are phase shifted by 1/4 of period. So both approaches are possible. Either you have one tape with just those lines, this is actually a lot easier to produce, and then you have a phase shift over there, or you have a phase shift on the field, and you have sensors that are aligned exactly like this, and then it works in exactly the same way. The signals are typically called A and B, and this is a relative sensor. So if I start at some position, I don't know where did I start. So for this reason we have this index. This is the third field. You can see that there is only one mark, and this gives me the 0 position. So there is a third sensor placed here, and when we hit the index mark here, we have this index signal, and we know exactly what is the position. Now this is a linear sensor, but you can make it also as a angular sensor, and I will show it to you on the next slide. Now typically this is a very accurate sensor. So the achieved resolution is in the order of few micrometers, and the range can be, let's say, maybe 10 centimeters, 30 centimeters approximately. So you can have fairly large distance, and you can measure with a very high accuracy. So it's not as good as, for example, the capacitive sensing. It's a few orders of magnitude resolution that is larger, smaller, but here we have a larger distance. Now if it's a linear sensor, now we have a problem with the thermal expansion. So when this scale is expanding, we change the distance between the lines. So this is changing with thermal expansion, and we may have problems with thermal expansion in this case. So we have one sensor like this in the labs. We were supposed to use it for the experiments, but we don't know if the labs will be happening or not. We can do this IRC also in a rotary version, and this is actually a little bit more common than the linear version, although both exist and both can be used in different applications. Now typically it is a wheel like this that has marks. Here those are the lines, the black fields and white fields. And we detect not just with 2 sensors, but typically with 4 sensors. This is due to, as we are trying to increase the reliability of the sensor. So we have not just 2 signals, A and B's, but we have more than 2 signals. But it works in exactly the same way. This yellow circle is the pair of a light source or a light detector. It can be done also in this way, where you have an LED that's producing some light and a mirror, and here you have the detectors. Anyway, we are detecting if we see the black field or if we see the white field in this case. Here is such an example. Here on top you see the code wheel of such an IRC. So here this gray field, if we would look on it under a magnifying glass or a microscope, we would see that this is not actually a gray field, but it has the lines. So there are very thin lines, and between the lines we have the transparent fields. So then from one side of this wheel we have the LED, it's producing light. From the other side we have the detectors, and we detect the passage of the light through the transparent fields. Now the typical resolution is very high. It's not uncommon to have sensors with 10,000 pulses per revolution if it's an angular sensor. But you can get sensors also with significantly higher resolution, so it's not very special to have something like 100,000 pulses per revolution or even more. So this is how the sensor looks like. Inside there is the code wheel and the electronic circuit. Here you have a shaft, and through a coupling you attach it to your rotating shaft, to your object. And here on this connector you have the ABC signals or index signals and so on. It looks also like this. The typical resolution is binary encoded, so typically it's something like 4096 pulses per 1 revolution and so on. So this is a very accurate sensor. It has a very fine resolution. It is used in precision machines where you want to measure very accurately what is the angular or linear displacement. It is not that expensive. The sensor like this, if it's a relative IRC, it might be something like, I'd say maybe $100 US approximately. So it's not very expensive. It's fairly common to have those sensors on a machine. But remember that this is a relative sensor. So this is a relative sensor, and it can measure only from some known zero position. Now, how to do it if you want to use it as an absolute encoder? We can use a very similar approach, but if it's supposed to be an absolute encoder, we want an absolute position. So when we power it up, we want that this gives us directly the correct reading without going to some reference position. On this picture you see such an example for a sensor that has only 4 positions per 1 revolution. So here this has a resolution of 90 degrees. So this sensor would not be very useful. This is shown here only as an example how this principle works. So again, we have a code wheel, but now we have 2 regions on the code wheel in this case. So here we have the internal circle and the external circle that's here. Now the yellow circles, they again represent the pair of LED and the light detector. And we are again looking for the light that is passing through the white field or through the transparent field, or if the light is being blocked by the black field. Let's say that if we are looking on white, then this would be 0, 0. If we would look on the black, this would be 1, 1. This is binary encoded, so we can see here that in this case, if we are moving the code wheel, we will move it like this. Then we first see that here we have white, then we would see black, white, black, and so on. So this corresponds to this part of the table as we are moving downwards like this. Now we can see that in this case, here at some positions, so we are changing just 1 bit. So for example, in this position we are changing this bit, and this bit stays the same. On this position we're changing from 0, 1 to 1, 0. So in this case we change both bits at the same time. Again, here we change 1 bit, and here we change both bits at this during the transition. So this is typically not how this is encoded. The way it's encoded is called a gray encoding. It's also a binary code, but now the states are rearranged in such a way that we have only the transition of 1 bit at a given step. So here we are changing this bit, here we are changing this bit, here we're changing this bit as well, and here if we go like this, we change this bit only. So we can see that if we encode it in gray encoding, then we know that at any given transition there is only 1 bit of a change. And if something goes with the sensor or with the signal, then we can detect this fairly easily, because here we will have a transition of more than 1 bit at a given time. So absolute rotary encoders, they use almost exclusively the gray encoding on the code wheel. Now this obviously is a sensor that has only 4 positions for 1 revolution, so that's not very accurate. But if we make more tracks in the sensor, we can have a higher resolution. So here you have such an example how this code wheel looks like. So we can see multiple tracks here on the code wheel. We can count them. It will be something like 10 or maybe even 12 bit encoder, and then the number of the resolution per 1 revolution is given by this formula 2 to the power of n, where n is the number of tracks. So this will give us the number of bits that we have available. So for example, if this would be 8 tracks, then 2 to the power of 8 is 256. So we would have 256 steps per 1 revolution. Now typically this is how it looks like. So this is an example of an absolute rotary encoder. We have shown here the resolution 1024. So this is a 10-bit sensor. So this has a resolution of 10 bits. So it would have 10 tracks here. Every track needs its own detector and an LED. So it's more complicated than the relative rotary encoder. But it has a smaller resolution as well. Usually the resolution of such an absolute encoder is about 10 times smaller than the IRC. So for the same price, but it may be even more expensive, but approximately for the same price you will get about 10 times lower resolution. So it's a trade-off between resolution, if you need it, and the absolute information that you have in this absolute rotary encoder. Now here we can see what's inside. So it's a little bit different design, but it's working in the same way. Here we have optical sensors that actually detect the angle of those position gears, and there is no this disc, but it's working in a very similar way. So this is an absolute sensor as well. So remember that this gives you an absolute position, but has lower resolution than IRC.